Ready, Brennan? Good to go, Bren?
Yes.
Okay, cool. Yeah, sorry, the
Okay.
mic now in my laptop, so that's why you probably couldn't hear anything. Um,
Okay.
okay, so welcome everyone. Thanks for coming to the network seminar. This week we have Brennan Klein from the Network Science Institute, who I had the very great pleasure of going to grad school with. And he's going to talk about network comparison and graph distances. So yeah, Brennan, thanks for coming, and go ahead and take it away.
Thank you, Tim. Tim didn't mention that we lived together for years. So if you ever want some good, I don't know, we don't have many good stories, but okay. Thank you very much for having me. Um, I was just telling Tim before this that a lot of my talks get like needlessly dogmatic about some niche concept. This is no difference. So it's on one level a very trivial concept, like quantifying dissimilarities between pairs of networks. On the other hand, it could also be profound. So I hope you enjoy it. I'm sort of assuming a rough maybe network familiarity and mathematical familiarity, but I was going to say if you have questions, feel free to just or clarifying questions, go ahead and interrupt me. But I don't know what the audio situation is, so maybe Tim can just text me if there's a
I
issue.
can shout at
Okay.
you if there's a question.
All right, great. So, just a quick little background. As Tim mentioned, I'm at the Network Science Institute at Northeastern University. I previously got a PhD in network science, and then prior to that, my background's very much coming from cognitive science and neuroscience. Um, I have to just do plugs because I must. So if you know of any loved ones in your life or colleagues or friends who are interested in network science, Tim and I both have a PhD in network science and we love it. You should come to Boston to do that. In the fall, we're actually starting a new master's degree program in complex network analysis. And then we'll be hiring a couple of postdocs in the near future. So keep an eye out. Last thing is not this summer, but next summer, you should all come to Boston for NetSci 2026, which will be the 20th anniversary of the flagship conference in network science. So I suspect everyone in the room and on Zoom is already aware of all of this. So I'm just going to continue. I usually just try to start by giving a quick background on my own research interests. So maybe you can kind of fit in how graph distances and network comparison kind of fits into this whole scheme. So today I'm going to be mostly talking about this paper. But there's a lot of other work that I look at around network reconstruction from time series data or information theoretic ways of optimizing the design of experiments, or more recently, quite a bit of agent-based models, and in fact, like software infrastructure for designing these what are called partially observed Markov decision processes. I'm the director of this lab called the Complexity and Society Lab. So on the one hand, I do a lot of research in theory of complex systems. On the other hand, a lot of my work falls in this public health or more and more recently, like a data justice lens. So in the pandemic, we did a lot of work on um, studying mobility patterns and how this maybe contributes to the spread or mitigation of COVID-19. Tim LaRock was very much involved with a lot of this research as well. Um, and we did a lot of look at uh, spreading in congregate settings or in schools, and more recently have started to get a lot of interest in the criminal legal system in the United States. So, anyways, I say all this just to say if any of this jumps out as especially interesting to you and not related to graph distances, I put my contact information on the slides. I mentioned I do this all with the lab, so a lot of the work that I'm going to be discussing today is in collaboration with these folks. And if you know people looking for postdoc positions, you should also have them reach out to me. Okay, so on to today's business. We will be talking about network comparison. I mentioned at the start that it is the most interesting topic in network science. Uh, I'm going to talk about a Python package that Tim Larock and colleagues and I put together to actually compute lots of these distances. I'm going to introduce an object that I quite like for kind of framing how a lot of these different graph distance measures could relate to one another, or how we can think about building principled graph distance measures. And then I'll talk about hopefully some teasers around what I view as maybe the state of the art and where this field maybe will be heading. Um, okay, so to get started, I'm going to ask a very simple question, which is just how similar, how close are these two graphs? Um, you may quickly realize that it's actually not a simple question. It's not even a well-posed question. It's like me saying, how similar are these two mugs, let's say? So you can think of similarity or closeness as how their positions differ. So on my screen, they're about 11 centimeters apart. You can think about how do their volumes differ? So how much liquid could they carry differently? Maybe how their temperatures differ, how their functions differ. And each of these questions has their own basically measuring stick. So you could measure position in meters, you could measure volume in liters, etc. And so I say this all to just say that there's a lot of ways to conceive quantifying dissimilarities between objects, period, mathematical objects in particular, and here today, graphs. So what I want is essentially this measuring stick. How far apart is this blue graph from this pink graph? And how do we even think about ways of quantifying this? So I'm just going to state sort of from the get-go what I think a a definition of a graph distance even is. I've used this term a lot in the 10 minutes of this talk so far. I haven't actually defined it. So I'm going to say that it's a dissimilarity. It's a scalar quantity that calculates the dissimilarity between a pair of graphs by measuring some distance between the descriptors of the graphs. So I'll kind of walk through each of these words. Dissimilarity here, I'm just going to talk about the graph distance measure. That's what I'm actually seeking. The descriptor of a graph is some observable of my random graph or of my graph. So this could be any number of things. It can be maybe better or worse properties, descriptors of graphs, and I'll get into what that intuition is in a moment. And then an actual metric. I need to, using these pairs of descriptors that I have of the graphs in question, I need to calculate some distance between them using a metric. Okay. I like starting here because you can kind of swap in a lot of different concepts for this. So I can think about the degree Jensen-Shannon divergence. So this is I'm going to shorthand it with the DJS. So my descriptor here is the degree distribution of both graphs that I'm looking at. And then the distance that I'm going to use is the Jensen-Shannon divergence between those two descriptors, and I will arrive at some number. That number tells me, according to this graph distance measure, how far apart they are, right? Now you might say, great, job done. The degree distribution is the only quantity we care about in graphs. That I might push back on and say, well, what about the actual adjacency matrix itself? How about if I know that I have the same size graphs, maybe I can just smush the adjacency matrices together and calculate how many ones and zeros are off place in that. I can measure some squared Euclidean distance as a way of computing how far apart they are. Or I can think about, and this is a colleague of Tim and my, Leo Torres, came up with this quite clever one, which is the non-backtracking spectral distance, which uses the eigenvalues of the non-backtracking matrix, computing a metric with the Earth mover's distance to arrive at how far apart two graphs are. And the more and more you kind of think through this, you can think about more and more descriptive descriptors and better or more and more suited distance metrics to actually combine such that you get a really informative, maybe most informative dissimilarity measure. But we'll get to that in a bit. So once we have this sort of framework, you can, like, these aren't the only three graph distance measures. There's, I mean, since we have published this paper and since I've even made these slides, I just was looking at the archive this morning. There's a new one about temporal embeddings. It's amazing. there's at the very least 20. There's probably twice as many. And in fact, there's an unthinkable number of them because you can combine any graph or any distance metric with any graph descriptor. And so in that world, like what do we do? Why like this seems just like an explosive problem. Um, it makes me sad. I don't want to work on this because there's too many options. So how do we even start? Well, we start by, first of all, getting together a bunch of your friends and putting as many as you can into an implementation called, into a Python package called netrd, which I was just checking this morning, has really taken off without me really realizing this. But what it basically has, so it's not necessarily a package that's completely designed around measuring graph distances. It, in fact, has a lot of techniques for network reconstruction and running dynamical processes on networks. But one maybe core and if it's just between us, most stable feature of this package is the graph distances module within it. So what it basically does is you say G1 equals this blue graph, G2 equals this red graph, and I can measure the dissimilarity using all of these different techniques between these two graphs. And it's quite simple. You just say, I want to measure the quantum Jensen-Shannon divergence between G1 and G2, and so I get this distance measure, right? So this I like this so much that colleagues and I decided to write a paper about all the different ways we could use it. And so this is it in action. Okay. So the paper that in question then is sort of getting at this notion of there's too many distances, I believe, and some of them are more or less informative than others, and there's no real benchmarks that we can point to say this one's actually a very good way to think about quantifying differences between brain networks or between infrastructure networks, or if I have a bunch of networks from one domain and I want to see how far apart they are from another domain, or how, in often case, as it often is, how similar they are to networks from another domain. How would I know about, how would I do this without any benchmarks? So that is where this funnily named WEGV, or within ensemble graph distance, comes into play. What it is maybe very informatively named. So it is the average distance between pairs of graphs with the same parameterization independently sampled from a given graph ensemble. So what that means in practice is it's a bit algorithmic. So actually, just to step back a bit, why is it usually done in these random graph contexts? For me, I think it's actually quite an ideal test bed to compare a lot of these graph distances. Because random graph models, like the number of facts we can just churn out about GNP or about preferential attachment models or about stochastic block models or some of these really well-studied graph ensembles, we know a lot about their properties and how their properties change under different parameterizations. So the motivation is maybe we can look for those key, maybe critical transitions in a graph ensemble and ask a question of our graph distance saying, can you actually pick that up? So this is where the game comes in, where let's say I like GNP. So it's a random graph model with n nodes, any pair of which are connected with probability p. So just to kind of give you a quick schematic of this. When p equals 0, it's an empty graph. When p equals 1, it's a complete graph. This is maybe the most well-studied object in network science and graph theory. So we can ask questions about, like, if I have some perfect graph distance, if I have my favorite graph distance, what should it look like as I vary the density, as I vary this p in a random graph model? And you can try this with your friends. You go to a pub and you draw on a napkin and say, okay, here's a new ensemble. Let's vary this parameter and let's measure the distance, the average distance between pairs of uniformly sampled graphs from that graph ensemble. So maybe you think, since it's GNP and maybe P of 0.5 is some maximum entropy, and it makes you think that this is the curve that you would expect to see as you vary P and measure pairs of distances between graphs. Or maybe you're like, actually, no, it should be a little smarter. Anyways, you can get into lots of fun and lose friends. And so this is an example of the distance I measured before, the degree Jensen-Shannon divergence. This is just like sort of hackily put this together, and in fact builds this kind of shape. But if you look at another distance measure, this is called the portrait divergence. This is a a distance measure that captures both paths of length L and degrees K of a graph. So it uses this graph portrait, which is a bit richer than just the degree distribution, but it also creates a within ensemble graph distance that maybe doesn't look like what you would maybe immediately expect. Or this new in 2017, graph distance called the D measure distance creates something that looks more like this. So I'm not to maybe editorialize about what is a good or a bad way that this should look, but at the very least gives us some common language to use when we're trying to evaluate these different measures. And you can do this again. So I'm just going to show a preferential attachment example. So this is a graphs of size n, where new nodes are joining the network and connecting their edges to nodes already in the network, proportional to those nodes' degrees to the function to the power alpha. So for example, when alpha equals -7, it's like anti-preferential attachment. When alpha equals -infinity, it forms this line. When alpha equals +infinity, it forms stars. And we know stuff about this graph ensemble such that we know certain phase transitions. We know when certain types of macro or mesoscopic structures should or should not emerge. You might say, okay, well, I know that when alpha equals 1, you get this emergence of scale-free networks, so maybe those should be super far apart from one another. But then but at 2, you get stars start to form, so maybe anything. So you see where this is going. You can play all these different games about what should an ideal graph distance measure actually capture using this within ensemble graph distance. And then we made lots and lots of subplots looking at lots of distances and lots of graph ensembles, just to kind of walk through a couple of them, just to give you an intuition about what we're actually looking for with these different models. So here I'm just going to show you 5 different distances, computing the within ensemble graph distance on GNP, G and average K, Watt-Strogatz models, soft configuration models, etc. So what you start to pick out is certain graph distances. So this net LSD distance, which uses spectral properties of the adjacency matrix, the Laplacian matrix, picks up this maybe critical transition when average K passes 1, when average degree of this ensemble passes 1. So it peaks there. So that says it's the farthest apart there, and then it starts to go down quite heavily. Or this non-backtracking spectral distance that I mentioned before captures some of the interesting phenomenology in Watt-Strogatz models. So it starts to measure pairs of graphs as being much farther apart when there's when the average path length is quite long, and then it measures them as quite close when this path length starts to decrease. And the clustering stays quite high, but then once the clustering starts to go down, you start to measure distances far apart again. And so on. So you start to see in these within ensemble graph distance curves, the signatures of the random graph model that you're actually studying. This is why I kind of think that this idea of a within ensemble graph distance per se is even useful. I think it actually, number one, can tell us whether we should keep or throw out certain notions of graph distances. Like if I know that I want a distance measure that can capture something about degree heterogeneity emerging in my graph ensemble, because I think in practice when I'm actually using these distance measures, I want to pick out something about the different degree distributions, then I shouldn't use a graph distance that can't capture the actual critical phenomena. So if you don't want to read the paper, you can just take a screenshot or mental image of this table. This is basically the whole summary of the table about whether certain distance measures that we tested in the paper capture these sort of known and important structural properties of the random graph models that we were looking at. You can do it like it was a hard sort of question about when to actually stop the paper. Like we could just include more graph distances, we could include more graph ensembles. We wanted to just kind of introduce this idea as being a useful one. So, and useful can be a number of things. So one is this is an example of a benchmark. The other is that in a sort of subtle way, actually just to go back, sorry to do this, but just to go back real quick, and this image from the netrd Python package, what I'm showing here is graph 1 and graph 2. And then I'm showing in a log scale, the distance between graph one and graph two under all these different graph distance measures. And if you notice, there's orders of magnitude between them. So maybe I don't want that. And maybe I want instead some sort of standardized notion. And here again is where the within ensemble graph distance can be quite useful. You can think of it in a way as a denominator, as a normalizing or standardizing constant between pair of graphs. And just to kind of motivate this intuition, think of this as a percentage difference ruler. So here's my original graph. If I randomly rewire one edge in this graph, you could imagine it's still a very close graph to my original graph, right? If I imagine rewiring 50% of the edges in the graph, it's a much less close graph than my original one, or 100% of my edges in my original graph are rewired, just completely randomly rewired, not taking into account any sort of degree distribution preservation or anything, then this builds this notion of a standardized graph distance. So how far apart on average is my original graph and its 100% edge rewired uh, uh, sort of null model graph. So this we're kind of cheekily calling the meter. I won't explain the joke, but it's essentially I have my distance. So the distance, according to a certain distance measure d between graphs one and two, can be standardized by taking the mean within ensemble graph distance between Erdos-Renyi graphs of the same size and density, the original graphs. This is just one maybe a feature of something like a within ensemble graph distance, right? So I talked a lot about descriptors. You can think of the descriptors as being as easy as simply the adjacency matrix, or as complicated as the eigenvalues of the non-backtracking matrix, and even more involved than that. And each of them have some well-motivated reason for why they're saying that this is why the graph distance I'm introducing uses this descriptor. I would say oftentimes like the notion of what metric do you actually choose to compute a scalar property or scalar value from the pairs of descriptors that you're looking at. Oftentimes this gets a little less love. I think it should get much more love because I think there's, in the same way that there's really well-motivated descriptors of graphs, there's very well-motivated distance metrics that you can use to actually get your final dissimilarity value. I, through Tim LaRock's former advisor, Tina Eliassi-Rad, was introduced to this book of distances, which is wonderful. I probably don't have to tell this to the Mathematical Institute of Oxford, but there's just some key properties of distances is that distances are non-negative, equality for x equals y. There's a distance between x and y needs to be a distance between y and x, so they're symmetric, and they obey some sort of triangle inequality. So in mathematics, that's what we want our distances to look like. The same holds for when we think about an appropriate graph distance. Just a quick note that this is just like a really cutesy thing. The authors were a couple, and several years ago, the European Journal of Combinatorics wrote a really nice preface to a special issue around how beautiful their distance level was. But also they had a lot of children who also do distances. So just a side note. Okay, so we have these four properties that I really like about distances in mathematics. I want to apply them to graphs, and I or maybe the field as a whole wants this preservation to hold. So it wants graph distances to be a metric such that they're non-negative, symmetric, and satisfy triangle inequalities. I hesitate a little bit about this one in particular, because if you think about it, this is actually quite a hard problem in graph theory. So a distance that satisfies equality only if graph one is equivalent to graph two has a whole lot of baggage associated with it, such that you might have to address some isomorphism questions. Okay, so and the common distances that this is just my sort of shorthanded way of thinking about distances that are often used in graph distance literature. There's everything as simple from Euclidean distances to sort of Jacquard or information theoretic Jensen-Shannon divergences or Earth movers distances. Um, I won't go into these too much, but and I actually unfortunately don't have a slide on this, but what you can actually do if you have a list of a bunch of graph distance measures is you can swap out the metric that's actually used to compute the distance value and perform some within ensemble graph distance experiments. You get actually qualitatively quite different results. But just as like a sort of, I mentioned that I'm going to try to cover some open questions and challenges. Um, this I think is quite a challenge to basically get down to the point where you have such a good graph descriptor that you're like, this is what I want to motivate my graph distance on, and then have it be kind of um, basically not stick the landing by choosing a distance metric that's not appropriate given your descriptor. There's more distances. There's a lot of distances. Okay. Um, so I had a little interlude about graph isomorphism that I actually don't want to discuss. So I might skip it, and if people are really sad that I skip a little discussion about graph isomorphism, we can talk about it at the end. But I do want to make sure there's time for a bit more like next steps and also some Q&A at the end. So this is just introducing what graph isomorphism is. Um, and that there is actually a family of graph distances that try to do basically a node realignment problem on graphs that have the same, on pairs of graphs with the same number of nodes. This is a very hard problem. There's okay ways to do it. And I think the most okay ways to do it are in this paper here, if anyone wants to check it out. Okay, so this is the fun part. Just going to introduce, these three things aren't actually out yet or really papers yet, but they're things that I've been thinking about. And I figured this is a really good chance to kind of hopefully excite people about a couple of different prospects on graph distance cinematic universe. One of them is using my favorite object called the DK series. And I'll go into a little depth of what I mean by this here. And then I'll introduce a notion of a between ensemble graph distance, so not the WEGD, but the BEGD. And then I'll close with just the idea that you could actually maybe learn the appropriate distance metric if I have pairs of ground truth assessments. So this is the part where if I were in person, I would say, can anyone raise their hand if they have heard of and already love the DK series? But I'm just going to assume you all have not and are about to love it. So the motivation of the DK series distance is on this descriptor question. And in particular, it looks at what we often, and this is sort of thrown around quite a bit in network science, but we often think of motifs as characteristic properties of networks. And when I say characteristic, that's a bit of like a maybe a technical term here because people often want descriptors of graphs that are characters. So you can, for example, just to keep bringing up this non-backtracking, the spectrum of the non-backtracking matrix, there's a lot of mathematics to point to up to a two core of your network. This is a characteristic property, so it's uniquely distinguishable of your graphs. So we want these like really rich information measures to use to motivate our distance. So if then motifs are characteristic of networks, why not build some sort of generic object that captures all of the uniqueness that motifs can do? And the motivation behind the DK series itself is to try to reproduce basic properties of observed networks. The motivation behind a DK series distance is that that's actually the most informative, potentially, way to compare pairs of graphs. So what this, just to kind of walk up, what is a DK series? Why do I care about it? Keeps talking about this stuff. Okay, so the DK series basically progressively builds a uh, I'll just explain it like this. So how many undirected one node motifs are there? It's just this one, the node, right? You think about all of the undirected two node motifs in graphs, it's also just this one. You can think about all of the undirected three node motifs or four node motifs or five node motifs or D node motifs. And if I were to enumerate and actually isolate all of the values of these motifs in my network, I would know quite a bit about my network. My motif distribution of my graph is quite an informative property of the graph itself. And so when I think about this DK series, I'm trying to look for uh, motifs of size D. But not only that, I want to know the degree values on all their stubs. What I mean by that is if I imagine the 1K series of this graph that I have here, the 1K series is motifs of size 1, so nodes, and their degree values. So if you kind of think through what that means, this is the degree distribution. So I'm trying to assign a probability of nodes of degree 1. So in this graph, there's just one. Nodes of degree 2. In this graph, there are 3. Nodes of degree 3. In this graph, there's 1. Nodes of degree 4, degree 5, etc. So I have the 1K series of this graph right here. And it is also the degree distribution. The 2K series is it's sort of building up from that. It's the joint degree distribution. So how many pairs of nodes that are connected have K1, the degree of node 1 equal to 1, the degree of node 2 equal to 2. If you look, there's just one of them. So you can kind of think about this object, this DK series, as being sort of more and more informative about more and more complex subgraphs and their connectivity of a network. So in just to kind of build this out a bit more, the 3K series is you have to look at two different distributions. So the triangle distribution and the wedge distribution, because there's two different motifs of size 3. So for example, the triangle distribution, there's only one triangle in this graph, and it has degree 1 equals 3, degree 2 equals 2, and degree 3 equals 2. Okay, I can do this with the 4K, and ultimately when I get to the 5K series, such that D equals N of this graph is 5, there's only one graph that satisfies this 5K series. So what I mean by that, if I were to sample from the ensemble that this 5K series prescribes, I'm only ever sampling this graph, this unlabeled version of the graph. So I can have different labeling schemes put upon it, but I'm only ever getting this graph out. So when D equals N, suddenly I get this really maybe over fit model of my network. And in fact, I get a lot more information about the graph. So if I sampled from the 3K series, I could get pretty close to my original graph most of the time, or 2K series gets me closer. And just to kind of play this out, and this is not necessarily what you should do in network science, but play this out visually. So just take this graph, for example. This is a graph of the autonomous systems from, this was about 20 years ago from a paper. And if I look at the 0K graph, so even below the 1K, the 0K is just the graph of n nodes and has the same average degree. The 1K graph starts to get some of these macroscopic structures. This is just to be clear here. The 1K graph means I compute the 1K series from my original graph, and I sample graphs uniformly from that distribution. And this is what one of them looks like. The 2K graph. See, suddenly already I'm starting to see more and more mesoscopic structures that resemble my original network in a really informative way. You can see where I'm going with this. So if I sample from the 3K series of my original network, I get something that looks, I don't know, like to my eye, quite close to the original graph. And so you can kind of put these all together and see the sort of rationale of what I'm trying to show here, which is that at the very least, the notion of a DK series captures a lot of rich information about my original network. And if I could use this to kind of spin it into a network comparison or a graph distance measure, then there's actually quite a bit of promise about where that might go. So just to kind of give you a sense, this is this column for the 3K. These are just the average degree, the radius, clustering, etc. You start to see between these pairs of columns, there's quite a bit of overlap between the actual graphs. So when I say how close or similar are these two graphs, I can say, well, can I compute the 3K series of the blue graph and the 3K series of the pink graph? And because there's two distributions, maybe I can measure some Jensen-Shannon divergence between these two graphs and arrive at some DK distance. I should note here that this a lot of this sort of intuition um and work is really led by a master's student who was working with me this past summer, or actually this past year, Elena Baumisters, who just finished her master's thesis, very much on this question of motifs and sampling motif distributions.
Brennan, we have a question.
Yes,
One. Is it relatively easy to sample from the DK series, or because you're conserving
great question. Sorry to interrupt. Yeah, go ahead.
Oh yeah, that was my question.
Yes, no, it's not easy. Uh, so I mentioned Elena's thesis. So this was a bit of a look into just how hard it actually is to compute. So, for example, there's a lot of work on the sampling the 3K series. Actually, just to back up for a second, when I say sample, I'm saying start with my original graph and perform a series of in most of the time edge swaps. So swap an edge between pairs of nodes I and J and pairs of nodes K and L, such that you preserve exactly the degree distribution, the joint degree distribution, or the triangle wedge distributions, etc. Once you get to 3K, number one, it's not shown to be ergodic, this approach for sampling, the edge swap approach for sampling. That said, also, Elena's thesis finds a sort of new way of doing this quickly. And what this opens up is a prospect of actually sort of separate from any sort of graph distance notion. You can sample a bunch of 3K series or even 4K series graphs in a way that you just couldn't do computationally before. So I think it's an exciting prospect in the world of sampling fastly or quickly DK series, but it is by no means easy. There's a question on Zoom as well.
Yeah. So can I ask you, before you sample, you also need to count how often the motifs appear, right? And counting,
Yep.
this is like homomorphism counting, right? And counting homomorphism is not easy. It's like computationally very complex, right? So how do you go about that if the graph is reasonably large?
Yes. So that's also a wonderful point. Like uh, slowly is the short answer. The bit longer answer is that and this is getting more into some other ongoing work, but you could imagine softening the DK series. So the DK series is quite rigid and precise, and with that precision, you get this inclusive property such that the 4K series contains all the information about the 3K series, which contains all the information about 2 and 1, etc. Um, but for example, what if I didn't have uh, between 0 and K max values of degree in my network? What if I had small degree nodes, big degree nodes, and medium degree nodes? There are some basically sacrifices that you can make in the expressiveness of the original DK series while still trying, and this doesn't solve the motif counting problem, but it at the very least solves the sort of combinatorial issue of counting all of the motifs of degree 1 to all the way to K. So there's little ways that you can chip away at with that. I think there's no world in which this is a graph distance for big graphs in the next couple of years, but basically it's just like it's limited by the fundamental limitations of how many or how big of motifs you want to count in your graph. But
Okay, thanks.
to just
Yeah.
sort of maybe sort of defend the point that I was just making is that you get a lot with just triangles and open triangles. So the 3K series is quite an expressive object, and it's not enumerating all 5 node motifs. That is a huge task, but it is much less than that. That at the very least, that's something that's exciting me.
Cool. Thanks.
Other clarifying questions on this? Okay, if not, I'm just gonna.
I think there was one in the chat just about applying this with hypergraphs also. But if you want to save it to the end,
That's a
fine.
great question. Yeah, I have no idea. I would love someone to do this, please. Okay. So real quick, so just the sort of natural extension of a within ensemble graph distance is an idea of a between ensemble graph distance. And here I think there's also reason to believe that this might actually be not just a cute thing, but maybe a useful thing. So if anyone is as old as Tim and me, maybe we remember this fun sort of discussion in the literature about how rare or common or appropriate it is to measure scale freeness in real networks. Just as like an example of one thing that you can do, kind of motivated by this exact discussion that we were having before, is if I have some real network data, and if I really believe that my graph distance measure is actually as informative as I say it is, and I have some generative model that I think well describes the system that I'm looking at, and for example, I can just try to minimize the distance. So I can span a parameter range, try to minimize, find the parameterization that minimizes the distance to my original graph. So in this case, I just made a toy example of nonlinear preferential. I mean, this is sort of by construction always going to work. But just to kind of illustrate, I made a nonlinear preferential attachment network of size 100 nodes, and the true alpha value that I used was 1.5. And if I just measure pairwise distances between graphs with -2, -1, 0, 1, etc., I'll find that it gets minimized at approximately the right answer. So in some sense, this is one way of thinking about model fitting using graph distances. There's a lot of caveats again here, because you need, number one, to have a sort of graph ensemble that you think is an appropriate one to compare against. Number two, you need a graph distance that's an appropriate one to use. We're not fully out of the woods, but at the very least, it shows some prospect. The thing I'll close with too, and this maybe you all have ideas about, because it confuses me a bit, but I think it's actually quite promising. So if I know with some metadata that a pair of graphs is far apart or is not the same, so you can think about maybe, and I didn't actually put this image in here, but there's a lot of these public data sets where, let's say it's connectomes of humans that have been diagnosed with schizophrenia or healthy controls. And so there's a labeled data set that says brain networks 1 through n are, or 1 through like 20 or 30 are controls, and the others are diagnosed with schizophrenia. If you measure pairwise distances between those, maybe the distance measure that you would want would say that the healthy controls are much closer than the between condition brain networks. If I didn't know what distance measure to use, but instead had some sort of expert annotation or some metadata, some ground truth assessment of whether two graphs are far apart, then I could do this thing called metric learning. So essentially finding some, this is just a block of text, so I apologize, but finding some matrix M that satisfies, or that basically, that satisfies this specific distance based on the input data that I have. So I could take something that's then out of sample and say, well, I learned this matrix M, and if I were to use this under this Mahalanobis distance, then the hope is that the matrix M will encode enough information about ground truth dissimilarity that some unseen new pair of graphs to compare can be evaluated. So that's one just example of what you can do. I was talking to a colleague recently who's looking at graph distances in the context of infrastructure networks. So if you knew like some sort of network structural representation of bridges in a country, and you knew some sort of network structural representation of like boats. This is a bit of a toy abstract example, but the goal of a metric learning experiment should say the bridges can be picked out as similarly bridge-like, and the boats can be picked out as similarly boat-like, and that you may find intriguing structural similarities between bridges and boats, but in order to do that, you would need some metric learning process to actually take place in the first place. So again, like this is not work that I've done, but it just is work that intrigues me, and I hope it intrigues you all. And I guess that is it. I didn't realize the slides ended here, but they do. I'm happy to take some more questions. I'm also happy to sort of answer some emails or if you want to reach out separately. But yeah, thank you all for your time, and over to you, Tim.
Thanks, Brennan. We have one question in here at least. So yeah, go ahead, Rohit.
Thanks, Brennan. This was super cool. Just because going off of what you just mentioned on learning a metric to optimize, on learning a metric to optimize some kind of known distance or known difference, what are the advantages of learning a metric, because it's not designed and therefore it could be some weird arbitrary combination of things you don't really understand, versus, let's say, calculating a shed load of distances that we do know and then maybe putting them on a decision tree or putting them on through some other kind of pipeline where it not give us perhaps more in a way to have distances that we understand and then combine them in some way to create a new measure of distance?
Yeah, I think that's a great question. My sensibilities, I think I share your sensibilities on it. So my intuition is that like an ensemble distance is actually much more appropriate form of like of if I wanted to smush together a lot of distances, I don't actually know how to do that appropriately. So maybe some sort of learning of coefficients or some sort of decision tree, as you mentioned. Um, uh, I think in my mind, there's some sense in which that's still a metric learning process, although it's maybe a bit richer than just simply learning an M with some Mahalanobis distance of labeled ground truths. I think they're similar sides of the same coin. I think it's like a bit silly of us to have so many distance metrics and not actually sort of assume that they're all informative in their own way. That said, I still do think because of these within ensemble graph distance experiments, there's actually just some that we shouldn't use. I'm not going to name them. You should do the experiments, but
Okay.
Yeah, I also have a question. So it's Renan. Very nice to thank you so
He can
much.
see you here also.
Okay, cool. So here you propose to evaluate distances by comparing, well, by looking at the variability across ensembles of graphs, right? Something that I wonder, did people also consider something slightly related, and that would be to try to characterize the robustness of a certain distance measure by looking at how a little bit of noise that would be added to a graph would impact basically the measure of distance. Because you could expect that if you modify, let's say, like a tiny fraction of the edges, it could be argued that the distance should be small, right? You could estimate the robustness of distance measures to different types of noise that would be added to certain graphs.
yeah, I mean, it's a great intuition. So I have done this in little exploratory ways. There's no, as far as I know, and I should not say there is no, but I have not seen like a sort of systematic look at this. I think when I'm imagining rewiring networks, it was mostly for sort of developing this intuition around a standardized graph distance. So like I can basically have a fully rewired version of my network, and that's if I use that as a denominator in some distance calculation, I get a standardized measure. If I rewire one edge randomly 1,000 times, and my distances kind of go all over the place or have some massive variability, I can imagine not wanting that, or maybe some sort of robustness to if I just rewire one edge from a hub versus one edge from a important high betweenness node. Maybe that breaks the distance in some way that's important, in a way telling you what the distance measure is actually picking up on, but also telling you about maybe some sort of normative or editorialized take on whether you should use this distance measure or not. I like the idea. I would love to do that as an exploration. And I should also just say, like, for stuff like that, I think one of the things that we were hoping for with this NetRD package is that, like, there's a lot of great questions that, like, so this paper right here was just like the team just kind of ran a bunch of for loops over and over again with our package, and I say this to say it was quite an easy exploration. And so a lot of these questions are actually quite fun, and you can get a lot of purchase out of what may seem like a really basic question, but it's actually quite informative.
You're making me really regret not being on that paper.
You know.
Another question about related to Renault's question about the denominator in the standardized distance right above Erdosh's head on your slide. Do you have to sample that, or did Harrison do some fancy analytic stuff so that you can like tell what the expectation of the distance is?
Yeah.
Or is it just something you have to take a certain number of samples to figure it out?
Wait, who asked the question?
Me.
That's a good question. Oh, for this little d, this is the sort of label of the distance we're using. So when little d equals Hamming distance or Jacquard similarity, we know this exactly. For others, we know it pretty much. Like, so for the degree Jensen-Shannon divergence, you know it quite well. It's a little boutique math problem if you want to find other distances where you can actually know analytically the denominator. I find so we actually have this in the supplement of our paper. We made the choice to kind of stop it at the easy distances because it was too hard. It was too hard.
Harrison ran out of cycles in his.
Yeah. Not enough coffee for that.
You have another one, right?
Yeah. Just a quick one. If I understand the DK series correctly, and I'm fairly sure I don't, is it that say when you conserve or when you sample from the 4K series, you are constraining more than the 3K series, which constrains.
Right.
Okay. So I wonder if there's a way, A, is it useful? B, is there a way to constrain, to choose the scale or the size of subgraph at which you're constraining, but then allow to randomize stuff that's smaller than that and stuff that's larger than that? Because here somehow you keep constraining, it's a funnel. But I wonder if we can make it, a funnel in both ways somehow. Is there a way?
So you squeeze it's randomness here. Yeah. That's a cool question. So as constructed or as defined, so a couple things. I think it's a really good intuition. One is that I think it actually isn't compatible with the current definition of the DK series, because what I specify by constraining the 4K series is I say all of the motifs of size 4 and the degrees of the nodes within those motifs. That necessarily entails wedges and triangles. I could say, well, I don't want all the motifs of size 4. I want 4 cliques, and I want open squares, and I want open paths of length 3. And maybe those are the only things I want to constrain when I sample. It's a good question. One of the maybe sort of like nearly tautological, but I think not, uses of a DK distance. So if I have the 4K distance of a graph, and I want to say, I bet if I sampled graphs with a 4K series, like with an asterisk where I don't care about some of like 3 of the motifs of size 4 in my network, so I only constrain or I only preserve the 4 cliques, the open squares, and the open paths. So I say, I bet I get most of the information about the graph by just constraining that. You can say like, well, how do you know? And I'll say, well, I have this 4K series distance that can tell me how close I am to my original graph in a sort of cannibalistic way where it's like, but you could do these like knockout experiments, or you could do a sort of Frankenstein. You want the 5 cliques with open kites in size 4, and so yeah, I think it's a great question. I think one of the things that is so sort of, to me, beautiful about this object is that you get this inclusive property, but that also comes at a cost, because if I know that I like simply can't count the motifs of size 13 in my graph of a million, like, then it's a beautiful object that I just can't use.
Yeah, fair enough. Thanks.
Yeah.
Cool. Are there any more questions online or in the room? If not, let's thank Brennan again.